For the following bond cleavages, use curved arrow notation to show the electronic flow. Okay, lovely. And classify each of them as homolysis or heterolysis. Identify the reactive intermediates produced as free radicals, carbocations or carbanions. This is a very valuable, very easy but a very valuable question because it gives you great insights. Now you have methyl peroxide, CH3OOCH3. Lovely. One must never draw without proper electron cloud. It has to be like this. I'll just eating away electron clouds is never any good person's intention. It's never a welcome activity. Right. Now, if you notice, what happens is one electron goes here and the other one goes here. More style, you should draw it like this. So the curved arrow must begin from the middle. It must end on oxygen atoms because one electron each. See, it is homolysis. One bond contains 2 electrons, and from these 2 electrons, one goes here and one goes here. So this is homolysis. Yes, this is homolysis. Why? Homo means similar. So the bond breaks up in an equal way, and this gets 1 electron, and the other one also gets 1 electron. Anything else? You get free radicals? Yes, you get free radicals. Done? Done. B part. Well, what happens? It seems that there is a minus charge here. Okay, and how does that minus charge arrive there? Actually, you know what happens is this. There is CH3CO CH3, right? If you remove H plus, because see, this OH minus has become H2O. What does that mean? It means that one H plus has been taken away and one lone pair is here. Right. So what has happened is, it is like this. Electron from OH minus electron pair has been donated. This bond breaks up in a heterolytic fashion. It has given away both the electrons to carbon, and that is why carbon has acquired a minus charge and a lone pair. Sometimes there are people who say that when you have already put a minus charge, why do you show the lone pair? Minus charge is just the formal charge. Lone pairs must be written very clearly and explicitly, and formal charge, it does not indicate a lone pair, it just indicates formal charge minus. Many a times, negative formal charge is possible even without a lone pair of electrons. So, lone pair should be very clearly identified and charges should be shown separately. This does not mean an extra lone pair, please note. This is it. So, do you see? This is the area when we are showing the bond breaking like this. This is heterolysis. And we have obtained an carbanion. Is carbanion? Yeah. Tertiary butyl bromide. It dissociates to give you tertiary butyl cation and bromide ion. How does this happen? See, this bond breaks. Wow, like this? Yes, like this. Let me show you lone pairs clearly. There were 3 electron pairs and now there are 4. This is heterolysis? Yes. And by this, you get a carbocation. There's a plus charge, so it's a cation, carbocation. Benzene ring plus electrophile is giving you a rhenium ion. Fine. How are the electrons moving? What is happening? Most interesting. See, this is the way we show it. Okay. This pi bond has been donated. Yes, indeed. And what has happened? You can imagine it like this. This is just imagination, but very useful one. You have a benzene ring? Yes. Just imagine that it breaks in this fashion. Wow. So what I get? I would get, is this heterolysis? Yes. And then you find that this E plus gets this donation. So what do you get? then you get this species. This one. So actually, the way you show it is this, but you should always imagine. I am showing you imagination bubble also. We don't write this, but this is actually what should be imagined. Pi bond jumps on one side. There is a heterolytic fission of pi bond. This was heterolytic fission of sigma. This is now heterolytic fission of pi. Plus and minus. Minus goes to donation. This is what you get. There we are. Right? So this is, well, homolysis? No, it is heterolysis once again. And we get a carbocation. A very different one. But yes, we get a carbocation in this again.